Take it away.
Hi, welcome to my talk about designing RFID implants. So what do I mean by that? Some people, such as myself, have RFID transponders installed underneath our skin. This talk is going to cover my journey to design my own implants, to work with an access control system that was not compatible with anything that was on the market at the time. It's also going to be touching on the basics of RFID, biohacking, and subdermal implant technology in general. Before we continue, I want to assure everyone that this talk will not have blood or gore type photos or even discussions. At the end, I will have some resources linked, and one of those is my YouTube, which does have some videos of like implants being put into me. If that's your kind of thing, go for it, but they're not going to be in the talk. The target audience for this talk is pretty much everyone. There are enough topics rolled into this talk that I hope everyone will be able to come away with some better understanding of either biohacking, RFID technology, and to some extent the journey of taking a product to market. Even if you've never heard of RFID or biohacking, you should be able to follow this talk. And even if you're an expert on all of those, I'm hoping you'll still get some enjoyment from listening about my personal experience. Who am I, anyway? Why am I talking about this, and how am I qualified to discuss any of this? My name is Miana, as was mentioned before. I'm a software engineer by profession. I also have ADHD, so my hobby is essentially collecting more hobbies. I have no formal qualifications in electrical or biomedical engineering, but I have spent a lot of time talking to people who work in those fields and reading things written by them. I'm sure I've annoyed a lot of them by now. Yeah, so as of right now, I have 26 implants installed. All of those have been over the last few years. I kind of got involved in this right at the beginning of COVID. A few of those implants I designed myself. Other ones are just things that you can buy on the market. One of them is meant for animals, not humans, but so be it. So yeah, I just want to give this talk because it's something that I'm passionate about, and I want to share my interest with as many people as possible. And I also discovered when trying to learn how to do this that there's basically no information on it. Apparently, there's not YouTube videos on shoving things under your skin that you got manufactured in China. But anyway, I better get started before I waste all my time talking about the talk. So, what is RFID? I want to make sure everyone knows what I mean when I use that term. It is an umbrella term for a bunch of specific technologies that use radio frequency communication, usually over very short distances. I'm sure everyone here has used some sort of RFID at some point in their life. In fact, most of you probably have an RFID card to get into your hotel room right now. My hotel card is here. But if you've ever scanned an NFC tag with your phone, or made a payment with your phone, or your contactless card, if you've ever used a key to badge into your office, that was all RFID tech. That's obviously not an exhaustive list. There's all sorts of RFID tech. One of my favorites that I come across day to day is just the toll booths in my area. They use a type of RFID called UHF. So when you drive under, it knows that it was your car and they can charge you money. So before I go any further, I want to expand some of the terms that I'll be using just so everyone's on the same page. RFID, as we just discussed, it means radio frequency identification. I feel the term's a little bit inaccurate these days because originally it was just transmitting an ID number that would then be looked up to let you into a door. Now there's much more complicated transactions that are happening, encryption, signing, all of that sort of stuff. It's not just purely ID, but that's the term for the whole industry, so there we go. LF and HF are just quick ways to refer to the resonant frequency of the technology. So low frequency is 125 kilohertz oscillating signals, and high frequency is 13.56. Doesn't really matter beyond that. That's just the selected things by the industry. Whoopsie. That is not the scroll button. There we go. NFC is a term that you'll probably be particularly familiar with. It's used with phones a lot. It's technically the name for a standard for high-frequency RF tech. Thanks to a common misconception, the term NFC is often used just as a full replacement for HF RFID tech, and RFID is used to refer to the lower frequency end of the spectrum. That's not accurate. NFC is a subset of RFID, but at this point that might have been a losing battle. Things like the Flipper Zero that a lot of you might have seen have a separate menu for NFC and RFID. NFC contains things that are not NFC technology, and same with the RFID. So I think that's a lost battle. Tag is the word that I'll try and use as the generic term for cards, fobs, implants, any sort of device that's being read, but I'll probably swap between all of those terms because I'm bad. Reader is a fairly self-explanatory term. It's the device that is reading the tag. It usually provides the power to the tag, all of that sort of stuff. I'll also probably throw out the term field, which is referring to specifically the electromagnetic field, the power transfer and the communication is happening in this technology. So how does it work? Well, you tap your fob to the reader and it reads the fob. Simple. Not quite. That's more of a 1,000-foot view. To dive a little bit deeper, there is a coil on the reader that acts as an antenna, which is basically a long, carefully designed wire, and an alternating electromagnetic field is created by pushing an AC signal through that antenna because of physics, and that's as far as I'm going into that. The tag has a similar antenna, and when the tag's coil enters the field of the reader, that fluctuating EM field induces a signal in the tag's antenna, and that energy is then used to power the chip. Once that tag is energized in a reader field, communication will happen by modulating that field. The exact way that's implemented depends on the frequency and the particular technology, but they all work under pretty much the same principle. So hopefully that gives people a basic understanding of the underlying tech. It's not that important going forwards. I just wanted there to be a standard knowledge going forwards. So what do I mean by implant? In this context, it's any device that is intentionally put inside the body for some purpose. But more specifically, RFID implants are what I'll be focusing on. They're usually, at least the more common ones, are small glass capsules that contain a cylindrical antenna and whatever circuitry is needed for the chip. These are the most common for humans to get, and they're also the only type that animals get usually. Usually in the back between the two shoulder blades if you're ever trying to find your cat or your dog's RFID chip. Slightly less common are what we often call flex implants. These are encased in a flexible polymer rather than glass. This is to allow them to be bigger because the glass capsules, once they get past a certain size, they become more fragile. Also, you kind of want some flexibility when it's going in your body. They also happen to couple much better with the large, flatter antennas that are in readers because most of this technology is designed to work with cards. So the little cylindrical antennas, completely different topology, completely different coupling factor in the physics. So once installed, other than any marks from the procedures, like little scars left over from the needle or anything like that, they're basically invisible. In this X-ray, you can see two of them. There's a glass one on the left in between the thumb and the pointer finger, and right next to it there is a flex implant. Specifically, that's one of the ones I designed. It's really weird that other people have circuitry that I built inside their bodies. That's never going to be normal to me, but this is specifically those implants, if you couldn't see them before. The glass one on the left and the flex one, at least the chip of the flex one on the right. But there are not just RFID implants. There are magnets. There are other inductive power technologies like Qi chargers. There's tritium, all sorts of things. I'm mainly going to be focusing on RFID implants, but I'm going to go over some of the other options while we're here, just in case people are interested in them. So magnets are my favorite. I have 8 of them installed right now. The ones in my hand are sensing magnets. What that means is they're small, and although they're strong for their size, they're relatively weak. The only reason I can pick up that much stuff is because those have magnets in them themselves. The main goal for the sensing magnets is for electromagnetic fields to make them vibrate right next to the nerves in my fingertips, and my brain learns, this means something different. So now I can tell when my microwave's on without looking at the light. Very useful skill. This is a tritium implant called the X-Glow. Only about 30 of them were ever made, and it is by far the dumbest thing that I have ever put inside my body. For those who do not know what tritium is, it is a radioactive material that emits beta radiation. It's very safe outside of the body. The encapsulation of the vial does block the radiation. It's completely background. But if it breaks, I'm probably going to have a bad time. I've had a few debates with people more experienced in this area than me. Most of them seem to think I will die, so I really hope it doesn't break. On the safer end of the more aesthetic things, this is a silicon subdermal infused with glow powder. Things like breast implants are pretty much the exact same technology, just without the glow powder. I have looked. There are not breast implants with glow powder, sadly. I have seen this used to make 3D shapes in skin, like I've seen people with skulls on the back of their hands where the skin sort of molds to it. That's not really my thing. I just like that if I point a flashlight in my hand, there's a glowing power button. Whoopsie. But yeah, there's also medical implants such as pacemakers, birth control. Those things tend to be more accepted day to day. I remember a friend of mine, when I was telling them about my implants for the first time, said, I'd never get one of those. It's like, don't you have a birth control implant in your arm that's like 3 times bigger than my biggest implant? That kind of changed her mind on the subject. But also, like, I myself have some medical implants, some of them that do extended release medication for me because, again, I have ADHD. Taking drugs twice a day is hard. But yeah, how do these things get inside the body safely? These implants are called subdermal implants because they sit just below the dermis. Essentially, they're sandwiched between the muscle and the skin. Before we move on to the next photo, I just want to warn people, there is a photo of a needle coming next. It's not got blood or anything like that, but if you've got a problem with needles, please look away. I'll tell you when it's gone. Most implants are installed with an ejector assembly like these. The white one is 2.1 millimeter implants, and the yellow one is 3 millimeters. Those are the really common glass implant sizes for some reason. And you use them, the needle is inserted very similar to a blood draw, but it's at a much more parallel angle to the skin because you're not trying to dive down into a blood vessel or anything, you're just trying to sort of slide under the skin. Often we pinch the skin up and push into the side of it so that all the blood vessels and everything are guaranteed to be out of the way. In the end, it's a very safe procedure compared to some other body mod stuff. The needle is then slowly withdrawn as the plunger is depressed, and that leaves the implant inside the pocket left behind the needle, essentially. There's also larger needles than what are displayed here, where you put the needle in, take it out, and then put the implant in, but I didn't have any non-gory photos of that needle, so. Alternatively, a scalpel can be used. This is that silicon power button from before. Oh, by the way, you can look, the needles are gone now. The line on the left-hand side of that is where an incision would have been, or was made with a scalpel, and then a thing called a dermal elevator gets put in. Sounds fancy, it's just a blunt piece of metal that lifts the skin up so you can slide something underneath it. Unlike the needle installs, these are often bigger and quite frequently need stitches or some other help keeping the wound closed. This leads me to some of the disadvantages of implants. It is a minor form of surgery. You're putting a foreign object inside your body, usually without a medical purpose in mind, and there are risks involved in that. However, the healing process is significantly safer than that of regular piercings that people get all of the time, and that is because unlike a piercing, the wound can close up just like after a blood draw, whereas a piercing, it's open for an extended period of time. Yeah, everyone worries about implants, no one worries about getting your ears pierced. Well, not no one. Not only that, RFID technology is a bit of a walled garden. RFID tags are often treated as single-purpose devices and are often considered to be disposable and even owned by the company that provided it to you. That's not inherent to the design of RFID tech itself, but it's more how the industry is developed. For instance, none of you would have probably gone to a hotel and been asked, hey, do you have a key that I can use to let you into your door? No, they just give you a key. And even if it's the exact same key as another building you have to get into, you're probably going to have a different key for that, even if the reader would be perfectly capable of reading it. This leads people, such as myself, to have multiple implants for different purposes, and often being limited to using them with systems that are either DIY or have vulnerabilities in the tech that allow you to clone implants, which very bittersweet is for me being an InfoSec person, being like, yes, the system's got vulnerabilities I can use. Oh no, it's got vulnerabilities. And it lets me into my house. And I'm not sure if this is a disadvantage or an advantage, to be honest, but it's really hard for someone to steal an implant. Like, no one's going to pickpocket my implant. They would need a machete. And hopefully that's not what someone's going to do to steal my gym badge. But I guess know your threat model. If you've got people who like machetes after your keycards, maybe implants aren't for you. One of the most common things I do get asked is, what about the TSA? Do I have problems getting through airport security? It's never been a problem for me or anyone else I know. With both millimeter wave scanners and the metal detectors, even with some relatively strong magnets inside myself, no problems yet. But what are the advantages to implantable tech? Unlike the disadvantages, this is a little bit more dependent on the particular person and the particular implant. So I'm just going to focus on some of the more common advantages that I see in RFID implants specifically for myself. So as I mentioned before, I have some fairly significant executive functioning problems. So to me, having my keys be part of my body is not just a convenience, it's a safety feature. I have been locked out in climates that were cold enough to be dangerous. That's not really a problem unless I already have frostbite, and I've lost that. And I know people have considered using this tech for like grandparents with Alzheimer's and stuff like that who would lose their keys. I believe the particular friend who wanted to do that ended up epoxying a RFID tag to their grandma's fingernail because they didn't want her to have to go through the healing at her age. But same concept works. And for me, knowing that I always have my keys with me is pretty much priceless. Beyond that, each of my implants has things that I do love about them individual, but overall, it's just really cool. Sometimes people ask me, is it just a gimmick? It's not, as I went over with some of the other things, but in some ways, yes, it is a gimmick, but it's not just a gimmick, it's really cool. It's also a form of self-expression in my eyes. It's not as visible as my tattoos or my piercings or anything like that, but it makes me feel happy, it makes me feel more in control of my own body, and that is another thing that I find priceless to me. But anyway, I think that's probably enough background information. I should really get to the headline topic, which is designing the RFID implant. So let's start off with why I did this. Essentially, it all boils down to me being very stubborn. I, in this situation, considered that a virtue. I had just discovered the world of implants and was doing my usual hyper-focus on the cool, new, interesting thing I found. And obviously, I needed to make my work badge an implant. And much to my excitement, and as I mentioned before, fair bit of disappointment, discovered that the tags used at work were vulnerable to cloning. Unfortunately, there were no implants compatible with this system, so I took the only option there was, obviously. There was no other option. I had to make my own. And decided, how hard can it be? And started working on making my own. As it turns out, quite difficult when you have no knowledge of electronics or PCB design or physics. But I got there in the end. So the first thing I had to learn about was the key elements of RFID transponders. At a high level, they're really simple, especially now that we can just buy ICs or chips that do most of the functionality. A talk on how the ICs work themselves would be great if someone wants to do one. That's not this talk. The IC or chip usually has two connections, one for each end of the antenna. The image on this slide is what's called a MOB package. It's really common for contactless systems. If anyone's got a transparent credit card or they've ever torn apart a credit card, you may have found something like this inside it. But there's also all sorts of other ICs that have different connectivity options and fit their specific needs. These chips also have an inherent capacitance, which is very important for what we'll be discussing shortly. The only other part of a tag is the antenna, which is, as I mentioned before, just a long, carefully bended wire. From an electronics point of view, calling it an inductor is probably more accurate. Together, this capacitor and inductor make what's called an LC tank circuit. By changing the ratio of capacitance to inductance, you can control the natural resonant frequency of this circuit. It's a little bit like when you rub your finger around the edge of a glass and it makes a humming noise. This electrical circuit also has a similar sort of resonance when current is passed through it. And all you need to know is how to change the inductance or capacitance. You don't really need to understand the physics behind this to make RFID implants, which is great for me. Now that I knew I needed to find a chip that could do what I wanted, and then correctly tune an antenna for that chip, I had a starting point. I could go researching. Unfortunately, it turns out the system that I was trying to make this for was an HID I-class system, which used chips that you cannot order online, which is what I've done for other projects. However, turns out I could buy the tags that they sell, the cards, and the tags have the chips in them. Well, not for long once I got hold of them, I guess. Acetone is very good at dissolving PVC, which is what the cards are made of. So leave that in a bowl for a while, and... Oh, whoopsie. Did I move past it? Oh, yeah. After I had extracted that, I get this coil. And at this point, I needed to work out that inductance and capacitance because I didn't have any of that information. To do this, I bought a cheap LCR meter. L stands for inductance in this case, and C stands for capacitance. So it was capable of measuring both the factors that I needed. Unfortunately, it's such a precise device needed to measure the capacitances and the inductances involved in this type of tag that it wasn't that helpful. So I tried to sanity check it by measuring the height, the width, the number of turns of the coil and stuff like that, and trying to back solve it from that math. After all that, I found the data sheet. Well, someone messaged it to me on Discord. I really wish they had done that like 2 weeks beforehand. But it was good to go through all that solving because it did turn out that I was very close to the real value that was listed in the data sheet, and this just confirmed it and made everything much easier going forwards. But if I don't find a data sheet in future, I know that this technique would work to find those values. So at this point, I have the chip I need, and I know the capacitance of those chips, and now I just need to work out how to make an antenna with the right inductance. There's a lot of math involved in that, I found out. I'm not particularly fond of math. I'm a software person. I get the computer to do the math. So there was a website that I put in the 2 values that I had, and it would solve for the third. So I knew the capacitance of the chip, and I knew the target frequency I wanted, which was 13.56 megahertz, because high frequency RFID. And then this cool website, which is linked in the resources later, spat out the inductance I needed. Then I needed to make a coil of wire that would have that inductance, which turns out is more math. In fact, in the real world, they would use simulation software that costs a lot of money, it turns out, to try and design these. But there are also papers that were written on how to ballpark estimate it for certain constraints. And I found some that matched what I was doing. And luckily, an electrical engineering friend of mine happened to turn one of those into a calculator as well, so I didn't need to do the math myself, which is also linked in those resources. With this tool, basically, I could put in various parameters to describe the shape of the coil, how thick the wires were, how many turns, all the factors that change the inductance of a coil of wire. One of the problems with this software is that tiny changes have a big difference, and it did not have any auto-solve functionality. It was type in the 10 parameters you need every step of the way, and if it was off by a bit, retype them all in again. One of my long-term goals is to change that software so it is capable of solving within certain constraints, but I'm very good at coming up with ideas, less good at completing them. So we'll see. So at this point, I know pretty much everything for my theoretical implant. I know the size and the shape of the coil, and I have all the parts. And this is when I had to work out how PCB design worked. Luckily, as I was saying before, RFID tags are really simple if you have an IC that's doing it for you. So I could just connect one wire from one side of the chip to the other. That's my schematic. Cool. Since then, my designs have got a bit more complex. I'm not talking about this one right now, but it's a work-in-progress implant for an RGB animatable 4-pixel display under my skin. I'll one day finish that, I hope. Once you have this schematic that shows you how you're connecting the chip, you then need to get footprints for the chip. As I mentioned before, the chip I was using is a really common one. I could definitely download a footprint for it, but because I'm so space constrained, I had to draw my own that only used part of the pin, the wings on each side of the chip to connect, because I just did not have enough space for the full thing. Then it's pretty much just a matter of designing the board. The way I learned how to do that was just watching an electrical engineering friend of mine design a board, and most of it seemed to click into place. Everything else was just Googling specific questions. I'm not going to go too far into that because it really depends on what software you're using. And it's also quite easy to learn. There's a lot of resources on the internet. Just to zoom in on the PCB design from that, you can see what I was talking about. I have the footprint in the center, and you can see why it had to be small, because otherwise it would crash into the coil. And the only real complexity about this, once I had done all the math, was working out how to join the top layer, which is the red, and the bottom layer, which is blue. When this is manufactured, all of this just turns into copper. And then the little green dots, they are what we call vias, and they show where the connection's going from one layer to the other. So at this point, it's more art than science. Everything that changed, such as the bend around the via, modifies it away from the ideal thing that the calculators I was using were assuming it would be. So I know everything I do here has an impact, but without access to simulation software, it's not really possible to do more than have a go. To get them manufactured, you export the PCB into what are called Gerbers. To me, they're basically just black and white images that represent the different features of the PCB. So on the left here, we have the Gerber for the top copper, and on the right we have the layer for the bottom. There was also one that showed the shape of the PCB itself, where to cut out, lots of files. All of that's handled by the software I was using. And then once I sent that off to a PCB manufacturer, I got a bag of antennas. These were ordered from a company called PCBWay, and they're made out of a flexible polyamide material. And that apparently is not a basic thing, so the minimum order quantity was around 800 units. That did not end up being a cheap hobby, it turns out. But now I have all the parts, I got to stick them together. I got this little hot plate thing and used some solder paste to connect the chip, and this is what it ended up looking like. That little black tab on the right-hand side is just to help peel off adhesive off the back, which makes it easier at a later stage of this process. Even though I had an implant at this point, it wasn't over. I still needed to do some testing. And although it did work first time, much to my surprise, I could only get it to work if it was in the exact right position. Like a millimeter to the left, didn't work. Millimeter to the right, didn't work. So that wasn't really gonna work if I implanted it in my skin and was just gonna wave my hand in front of a door willy-nilly. So I had to work out what was wrong. This is when I spent more money and bought a thing called a vector network analyzer. With this, I could determine the peak frequency of the antenna. Basically, what it seems to do, from my understanding, is it scans the spectrum, and wherever it experiences the most loss on its of voltage from the coil, is where the reader was being able to pass the most voltage over to the chip. It's not really loss, it's how much power the chip could receive. From that, I then went back to that calculator I used to calculate the inductance in the first place, but I put in this new resonant frequency I knew and the capacitance that I knew, and worked out, like, I basically back-solved what the inductance must be. It's not quite accurate because there's also some stray capacitance in the circuit board, but for me, that's basically impossible to estimate. So I calculated what I thought the inductance would be, compared that to my original calculations, worked out an error factor essentially, and then used that to adjust the original design. In the end, I just made the coil longer, essentially, until it had made up that error margin, and that worked. This trial and error method definitely did work, but now I add an extra capacitor called a tuning capacitor. It's basically, because the frequency is determined on the ratio between the capacitance and the inductor, I was trying to get the inductor perfect first time. Not really a good approach. Having a capacitor there means I can add additional capacitance, and then if I try and deliberately undershoot the target frequency, I can add additional capacitance to bring it up into line without having to wait several more weeks and spend several $100 more on 800 new boards. It also gives more flexibility for the inductance that we need to target. I recently worked with a chip that had a really, really low capacitance, so it needed a much bigger coil, or I could just add a capacitor, and that made it much easier to design. At this point, all I have is a PCB. It's much smaller than a standard RFID tag, but it's still a PCB. I can't shove it in my body yet. So it needs some sort of coating that keeps the fluids away from the electronics and the various metals in there away from my body. To be clear, this step is only necessary if you do want to make implants. Everything else is still applicable to PCB design, RFID tag design. I've seen people embed these in resin and all sorts of other things. Personally, I had no interest in solving the biosafe problem myself. More than happy to leave that up to professionals. There's a company aptly called Dangerous Things that mainly makes and sells implants, but they also offer encapsulation services to people like me. So I send them the implant and they sent it back to me covered in biopolymer. This is what the implant looked like after it was coated, and at this point I decided to call it a flex class because it's a flexible implant for I-class. Very creative. And at this point I was pretty much ready to implant it. Although I'd done some implant installs on myself, and to be clear, I really do not recommend people do installs on themselves, this is something that's going to require a scalpel, especially given I decided to put it in the back of my finger. So I went to a body mod specialist, essentially a normal piercing shop, but this person had experience with implants. And yeah, it healed perfectly, and as you can see, there's a silhouette of it in the middle of my finger. So it's built biosafe and in my body, but does it work? Yes. This is where now flipping the bird opens doors for me, which is where the title for this talk came from. I will mention, if you intend on doing this, even if you have permission, please get it in writing. I definitely experience what we'll call office politics problems from this little project of mine. So what's it like to actually use? Basically, if I rubbed it in the exact right spot, as you can see me sliding my finger over, it would work. The performance wasn't as good as I had wanted. One of the problems with my methodology using the VNA to test the frequency is that's not its target use case. So these readers have slightly different characteristics. I probably should have also included testing on the actual end product before I put it in my body, but it worked. The only problem this has caused is that, the readers that we had at work that had keypads in them, my implant didn't work with those because the keypad was in front of the antenna, and that made the distance too far for it to be able to read it. Well, unless I sat there for 5 minutes. But so yeah, there were definitely lessons learned from that process. As I said, I would test the device on the real world devices I want it to interact with, but those aren't going to give me the same measurements I need, so that would really be an additional factor. Also, if I could get access to the simulation software and the training to use it, that would really make my life easier. But yeah, if anyone's thinking about doing a project, if anyone wants something and they can't find an existing product to do it, just do it yourself. Like, most of my philosophy for this stuff is essentially, the fool did not know it was impossible, so she did it anyway. And like, I've had a few failures, but also all of them have taught me stuff and it's been fun. Even if I hadn't got an implant out of this, I still think it was a valuable process. So what's next for implants in this space? I'm going to go through some work-in-progress projects. This is the what I call the Lit-AF Flex RGB. Those ones don't actually have RGB lights in the photo. I haven't got around to making it. That was the schematic that I showed you earlier to show that my schematics are more than just one part these days. And that's basically just trying to provide power, communication, and a microcontroller, and I'm going to open source all of that. Mine's going to be used to control RGB LEDs, but I've heard people talk about the idea of putting glucose sensors on there and stuff, so hopefully that happens. This is a project called Body Bytes. We're trying to use Qi chargers to power a little Linux computer implant. That's already been done. This is called a peg leg. It's literally a Raspberry Pi with an inductor coil that someone stuck on their arm. There's been quite a few of those, and it works really well. It's quite an old project, and I find it fascinating, but it's a little bit unwieldy. I wouldn't want one myself. This is my current latest project. This is using a Qi charger to power a light. I've got a firefly tattoo on my arm. It's going to go under that. I wanted it before this talk, but that didn't happen. But it does work, and it's got around 250 lumens of light output. I'm probably going to get burnt. Oh, there's the tattoo. I forgot I included that. This is a payment implant that a friend of mine's working on. This is another project of mine where we're trying to make like accessories, like bracelets and stuff that can power the LEDs. Basically, all sorts of things that people want to work on. If you want to get involved, there is a Discord community. This QR code doesn't really matter. It's in the resources later. I'm pretty much out of time, so I'm going to skip this section. Basically, I want to thank the biohacking community in general for inspiring me to do this sort of stuff. Corey Lord, who is an electrical engineering friend of mine, who specifically inspired me to work on implants. Daniel is another electrical engineering friend of mine. And then the RFID hacking community and various other people, as well as the DEFCON goons and all the attendees. Just thank you so much to everyone. It makes it really rewarding to do this kind of stuff. But yeah, if you want to contact me, feel free. That's also in the resources link, so I'm going to leave this one up for a second. This has links to the calculators, to the slides, to the Discord, anything like that. It's doitfor.science/DC31/resources. That will also get you to the page. I don't know how much time I have left. If anyone has any questions. Yes, MRIs are completely safe for the RFID implants. They've been tested up to 7 Tesla MRIs, I believe, without any problems. The magnets is debatable. There are the techs that the techs that run the MRIs would probably not want you to go in one. I know people personally who have gone in them, and they experienced minor discomfort, and that was all. However, like I have one in my ear. I would have to have that one taken out if I was having a head MRI, because you would not be able to see the picture anymore because there's a magnet in my head. So, but my time is now up. So, goodbye. Thank you very much, everyone.